Hello and welcome to this video where today we're going to be looking at the nuclear radius and how you can actually calculate the size of nuclear radius. So we're going to start off by looking a little bit more in detail at Rutherford's experiment and electron diffraction and look at the pros and cons of both, and then we'll have a look at how you can actually work out using these experiments the radius of a nucleus of an atom. So we saw in Rutherford's experiment last time that we basically fired alpha particles in, and he was hugely shocked to find that these alpha particles were repelled by large angles, and he was able from that to actually work out an approximation of the size of the radius of a nucleus. So here we've got a nucleus and here we've got an alpha particle. Now what basically happens is if we take this alpha particle a long way away from the nucleus, we're shooting it in, it's got a certain amount of kinetic energy. So out here it's got all kinetic energy basically, so it's all kinetic like that. As it moves in though, it'll slow down, so it will lose kinetic energy, and the reason that will happen is because this is positive and this is positive, and so therefore there's a force in this direction, so this thing will accelerate in that direction, and so therefore the velocity increases. As that happens, the kinetic energy goes down, but then the electric potential energy stored in the field between these two objects increases until they get to a stage where they are as close as they can get, and at that point the velocity becomes zero and all of the energy is then stored in the field as electric potential energy. So here it's all electric potential. Then what will happen is, because there's still a force in this direction, this thing will then accelerate out here, and eventually all of the energy will then be kinetic energy again. So we can use that fact and an equation from Unit 4 to actually work out the distance, the minimum distance between our nucleus and our alpha particle when they are as close as they can get. So we know, for example, we've seen that the kinetic energy out here is equal to the potential energy at the closest point. And we also know that the electric potential energy is given by this equation here, where V is the electric potential due to this object, because the alpha particle is in the electric field of this object, multiplied by the charge on our alpha particle. And we also know that the electric potential for a charged object, is equal to a constant multiplied by the charge on that object divided by the distance you are away from that object, assuming that all of the charges is at the center of this particular object. So we can put these together. If we put these two together, we end up with the potential energy is equal to this equation, so is equal to K Q over R, so that's your V, multiplied by Q, so we'll pop that here now. So the electric potential energy stored between these two charges is given like this. And we know that all of the electric potential energy here is equal to the kinetic energy that it started off with, which we can actually measure. So we can measure the starting kinetic energy of these things fairly straightforward. So if we tidy this up just a little bit, then we know that the kinetic energy is equal to the constant multiplied by the charge of our alpha particle multiplied by the charge of our nucleus divided by the distance between them. And it's this thing that we want. We want to know how close this thing can get. And if we rearrange it, then we end up with this equation that's over here. So the radius is equal to our constant, which is 9 times 10 to the 9. You then take the charge of your alpha particle, your charge of your nucleus, and you divide it by your kinetic energy, which you can measure from the start. Okay, so obviously there's a big issue with this, because we're not now measuring the radius of the nucleus. What we're doing is we're measuring the distance between them, and obviously the closer we can get our alpha particle to here, the better measurement of our radius we're going to get. So the kind of things you would be asked in an exam, so we've got an alpha particle, it's projected, it's got kinetic energy of 4 MeV, and it's projected directly towards the nucleus, and the number of protons in this particular gold atom is 79. Well, it is in every gold atom, because that's what makes it a gold atom. We want to calculate the closest distance between these two particles. So this is our equation we had before. We basically just use the numbers that we've got. So we take, but the very first thing I have to do is I have to be very careful with this, because this thing only works if this is measured in joules. So I have to convert that into joules. So I know that 1 MeV is equal to 1.6 times 10 to the minus 13 joules. So therefore 4 MeV is just 4 lots of that. So that's equal to 6.4 times 10 to the minus 13 joules. So that's my energy. So this is the energy I'm going to use. So now I'll put all of my numbers in. So I've got my constant, so 9 times 10 to the power 9. The charge on our alpha particle, well, the charge on an alpha particle, it's got 2 protons in it. So it's got 2 lots of 1.6 times 10 to the minus 19 coulombs. Multiplied by the charge of our nucleus. Well, that's got 79 protons in it. That's got 79 lots of 1.6 times 10 to the minus 19 coulombs, divided by the kinetic energy, and the kinetic energy is what we've just worked out. So 6.4 times 10 to the minus 13 joules. And if we do that on our calculator, we end up with 5.7 times 10 to the minus 14 meters. And very often we express nuclear distance in terms of femtometers, where 1 femtometer is equal to 1 times 10 to the minus 15 meters. So this would actually be 57 femtometers. Now, just as a comparison, other experiments have been done on gold, and the agreed the agreed radius of a nucleus of gold is actually 6.5 femtometers. So if you compare the 6.5 femtometers, the sort of accepted value with our 57 femtometers, this is nearly 10 times bigger than this. So this approach isn't particularly accurate. However, there are other ways that you can work out or measure the size of the radius of a nucleus. The other one is electron diffraction, and we kind of mentioned this in the very first video. Electron diffraction experimentally works very much like alpha, like the Rutherford experiment where you used alpha particles. You basically take an electron source, you fire electrons towards your sample. Again, in this case, we're using a thin gold sheet. As it goes through, if you've chosen electrons with the right amount of energy, they'll have a de Broglie wavelength that's comparable to that of the nucleus of an atom, and so they'll diffract around the nuclei. And so what you'll end up with a diffraction pattern, just like you saw in Unit 2, where you'll end up with, for example, a bright bit here, and then a dark bit, and then another bright bit, and a dark bit, and then another bright bit, and the same on this side. And so you can actually draw a graph. You measure the electron intensity, basically how bright in a way, but basically the number of electrons. So there's lots of electrons going through here, not many here, more here, not many here, and so on. So here's your first peak, so when the electrons are going straight through. As you move this round this angle, what you find is that the intensity goes down, so the number of electrons is a minimum here, and that's in between the middle of these two here over here. As you move the detector further around, then the intensity goes up and then back down again. And so you can measure this angle at which the electron intensity is a minimum. You can then do some really quite complicated maths that we don't really need to have a look at all. But if you do that, then you'll find that this angle, or the sine of this angle, is related to the de Broglie wavelength, and you'll remember that from Unit 1. And that's given by this equation here, where h is Planck's constant, m is the mass of an electron, so that's the mass of an electron. This is the velocity of our electron, and then this is the de Broglie wavelength. So if we can work out the velocity of our electron, which is actually fairly straightforward, then we can work out what the de Broglie wavelength is. And then this thing is what we want. So this is basically related to the radius of the nucleus. Okay, so it's basically, give or take, is basically the size of the object that the thing is diffracting around. But it'll give us an idea. From that we'll be able to work out the radius of our nucleus. So we can work that out. The velocity of this thing is fairly straightforward, because if we know the kinetic energy of these things, which is given like this, and we accelerate these through a potential, then the work done accelerating it through potential is just given by the charge of our electrons multiplied the potential we accelerate it through. So we know the mass of the electrons as well, so we can work out V, which means we can plug it into this equation, which means we can work out lambda, and we can take that and then plug it into here, and then finally we can work out by rearranging this equation, we can find out kind of the size of the object that's doing the diffracting. So this equation, you don't have to remember this. Having said that, there was a 6-mark question on this in the new specification a few years ago, and this was mentioned in the mark scheme, and we'll have a closer look at that in a second. So perhaps it's useful just to remember this, if you're asked about electron diffraction and look at and trying to work out the size of the nuclear radius. So let's compare these two methods of actually trying to find the size of the nuclear radius. So we'll look at alpha particles first. We'll look at three things: basically how it works, how accurate this thing can be, and then pros and cons, advantages and disadvantages. So if you look at alpha particles, they work via Coulomb repulsion. Basically, you've got two charged particles, they're like charges, and so they repel each other. As for how accurate they can be, well, they're not particularly accurate, because basically what we're doing is we're finding the distance that the alpha particle gets to the nucleus is basically the nearest point. So that gives us the upper limit. It gives us the maximum size that the nucleus can be. It's probably smaller than that, but it's kind of like it gives us the biggest number that this particular nucleus can be. Something that does affect the accuracy of this is that the alpha particles have a size associated with them, and then so does the nucleus. Our analysis of it assumed that they were both point charges. Because they're not, obviously that will make a difference to the accuracy. What else will make a difference to the accuracy is actually how we do the experiment. If we have lots of kind of gold atoms, then we'll potentially get lots of scattering, so we'll not be able to measure our angle properly. And if if our alpha particles are not monoenergetic, in other words, they don't all have the same energy, they'll be deflected by different amounts, and so therefore our angles won't be consistent, and we won't end up with a particularly accurate result. As for pros and cons, again, a disadvantage of this is that the nucleus recoils. We've assumed that it basically stays there as the alpha particle comes in. Alpha particles are nuclei in themselves. They're helium nuclei. They're quite small compared to a gold nucleus, but even so, as it approaches, there will be a small repulsion for the gold nucleus too, and we haven't taken that into account, so that's a disadvantage. Another disadvantage is the fact that both of these things are really hadrons. They're made up of protons and neutrons, which in turn are made up of quarks, and all of those interact via the strong interaction. So if our alpha particle gets too close to the atomic nucleus, this strong interaction is going to start to play real havoc with all of our results, because you'll have an attractive force going on as well, and it'll all go wrong basically. So that's a big disadvantage. So this works really to give us an idea of how big nuclei are. It doesn't give us a particularly accurate result because of that. Electron scattering, on the other hand, or electron diffraction, is actually much more accurate. We've seen how it works. It's basically electrons diffracting around the nucleus. They have a de Broglie wavelength, which is why they diffract, because they have a wave-like nature as well. You measure the first minima of your intensity, and then you just use this equation. In order to get your experiment as accurate as you can do, you need a high kinetic energy. The higher the kinetic energy, the smaller the wavelength of this thing. So the smaller the wavelength, and you want a small wavelength because you want the wavelength to be approximately the size of a nucleus, or approximately in the order of like a femtometer or so. So you have to have high kinetic energies to do that. So if you can accelerate these up to high kinetic energies, you'll make your experiment more accurate. Again, it suffers from the problem of multiple scattering, because if you've got lots of gold atoms, then it potentially will diffract around lots of things. Also, if your electrons are not monoenergetic, in other words, they have lots of different energies mean different velocities, which mean different wavelengths, and so you'll end up basically mixing up. You'll get a very spread out sort of pattern. It'll be really hard to actually see what's going on. In terms of pros and cons, this is good because there is no strong interaction. Basically, electrons are leptons, and again, that's something that you would need to mention in any answer to do with this. So electrons are leptons, so there's no strong interaction, and so there's no kind of messing around with any attractive forces or anything like that, at least from the strong interaction. The problem is that the first minima is often difficult to see. Because you've got other atoms, other nuclei around, then superposition kind of starts to get a little bit mixed up, and it's actually quite difficult to do this experiment. However, it is possible to do it, and if you can do it properly, then this is actually more accurate than that because of these reasons up here. So that's what people have done. They've done this, they've done other experiments with neutron diffraction and things like that, and they've had a look to see how the radius of a nucleus changes as a function of the size, well, of the atomic mass number, basically. So A is the atomic mass number here, so that's atomic mass number. It basically tells us the number of protons and neutrons. So the A is the total number of protons and neutrons in our nucleus. And what this is really saying is that this is, so the radius of our nucleus, this thing here, depends upon some number. R0 is just a constant number, and it depends upon how many protons and neutrons you've got, which kind of makes sense because you'd imagine if you've got more protons and neutrons, then your radius is going to get bigger. So people have done this experiment for lots of different values of the atomic mass unit, and they get this graph here, and it just happens to fit with this. So what we're saying is that the radius is proportional to the atomic mass number to the power of a third. Now these graphs are hard to work with, especially if you want to try and work out what this value here is. So there's two ways to do that, and you need to know both ways. Basically, if you take this, and if we write down the equation for a straight line, like this, and we kind of identify each term, then if we plot r on the y-axis and we plot a to the third on the x-axis, we should end up with a graph where this is equal to 0, so there's no y-intercept, and the gradient of our line equals this number here, this R0, and that's exactly what we get. So this is this graph, and we've transformed it in exactly that way. So we've plotted a to the power of a third against R over here. You get a straight line, it goes to the origin, and if we worked out the gradient of that, it would give us a value for that. Here R is measured in femtometers again. So again, we can actually work out what this constant is. The second way to do that is slightly more complicated. Again, it's something you need to know. So we can transform this again into a straight line, but in a different way. So if we take logs of both sides, I'm going to use logs to base 10, but it works equally well with natural logs. If we take the logs of both sides, we get this, a to the third like that. Oops, a to the third. We can then separate these out using our log laws, because we know that log of a times b is the log of a plus the log of b. So that's equal to the log of R0 plus the log of a to the third. And we know if we've got log of something to the power of something, we can take the power and put it in front. So that's equal to the log of R0 plus a third, that's meant to be 3, a third log of a. And if we rewrite this, we end up with the log of R equals, and I'm just going to swap these two around, is the log of, so 1/3 the log of a plus log of R0. And again, if we associate this with a straight line, we get y equals mx plus c. If we put y on the log of r on the y-axis and log of a on the x-axis, then the gradient should always be a third, always, 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 because of this power up here, and the y-intercept, so this number down here, gives us the log of R0. So if we want to know what R0 is, if we do a y-intercept to the power of 10, then that'll tell us what this R0 is again. So we've got two ways of actually making sure that this thing's right. Basically, we can do a nice easy plot of a to the third against R, where it gives us a gradient of this, or we can take logs, which is a bit more complicated. But basically, we end up with the same thing. So, for our next step, we'll have a look at actually how we use that equation. This is fairly straightforward. So I've got a gold nucleus. It's got 197 protons and neutrons, and I know that when I've done these experiments, the radius of this nucleus is approximately this number. I want to know what this is, this R0 thing over here. So I write my equation down just like I normally do, a to the third. I rearrange it, so I get R0 equals R over a to the third, and then I just put my numbers in. So the R, I've got my question here, and then I divide it by a to the third. Well, a is 197, and I take the third power of that, and if I do that on my calculator, I end up with 1.2 times 10 to the minus 15 meters. And really, this R0 is not, there's no formal definition of it or anything like that, but what it does tell us is it gives us an idea of basically the radius of one proton or one neutron, really. So this thing's related to the radius of a proton or a neutron, and it's given by this number here. You get different numbers depending upon how you do the experiment. So sometimes it's 1.2, sometimes it'll be 1.4, but generally it goes between 1.2 to 1.5 femtometers. So if you do this calculation and you get numbers that are massively different from that, then you've probably done something wrong. So finally, what we can then do is we can do something quite interesting. We can basically say, okay, we know how we can work out the mass of nuclei actually fairly straightforwardly. If we know the number of protons and neutrons, and we know the mass of a proton and a neutron, we can work out the total mass. Now, because we know the radius of these things, we can actually work out the volume. And so if we know the mass and the volume, we can work out density. So if I want to know the density, I do mass divided by volume. The mass of a nucleus is simply equal to the number of protons and neutrons I've got in total, which is the A, multiplied by the mass of one proton or neutron, which we're going to call U. Now, U is called the atomic mass number. It's got a proper correct definition, which we'll come back to in a later video. But basically, it's the mass of one proton or neutron. The volume, we're going to assume this is a sphere. So if it's a sphere, the volume of a sphere is 4/3 pi r cubed, like that. But we also know from our previous slide that r is equal to r0 a to the third. So if we put all of these things together, we can work out what this density is. So if I substitute everything in, I get density is mass, which is AU, over volume, which is 4/3 pi r cubed. But r cubed is r0 cubed, and then I've got a to the third cubed, which is just a. So if I substitute that into here now, I get AU over 4/3, and r cubed is r0 cubed a. Now I've got an a on the top and an a on the bottom, so I can cancel those out, and so I end up with my density being equal to U over 4/3 pi r0 cubed. And if you want to, you can make it look a little bit neater. I'm dividing by fraction, so that's the same as multiplying by 1 over the fraction, so I get 3u over 4 pi r0 cubed. Now you might go, okay, that's fine, I can work out the density. But if you think about this, this is just a number, and it doesn't change depending upon what nucleus we've got. So that's a constant number. Obviously 3 is a number, 4 is a number, pi is also a number. This r0 again should be a constant. So what we've got is we've just got a whole bunch of constants here. So in other words, the density, the nuclear density is also a constant. In other words, it doesn't matter whether you've got a small nucleus or a big nucleus or a medium-sized nucleus. The density of all of those nuclei are always going to be the same. So the nuclear density is always the same. And if you actually put your numbers in, you end up with something like 3.4 times 10 to the 17 kilograms per meters cubed, which is obviously a very, very dense thing. Here on this slide, I've just tied it up, so you've got all your equations. You can see actually how they go in. You cancel your A's out, you end up with that. And as I say, density is independent of A. In other words, it doesn't matter whether you've got a big nucleus or a small nucleus. So there's a lot of information on that video, so I suggest you go back and have a quick look at it again. But basically we compared our two ways of actually working out the nuclear radius, and then from that looked at two different graphs and how you transform the curve into two straight lines. And then after that, how you then take those numbers and you use them to show that the density of a nucleus is independent of the size of the nucleus, basically. So that's that for nuclear radius. Thank you very much for watching, and I'll see you again soon.